Okay, so today we are gonna finalize the comparators topic. So we will see various comparator architectures, and we will talk about regenerative comparators a bit more to solve some examples. So the main problem for a comparator, or not the main problem, but one of the main parameters is the driving capability, because we want, of course, high speed. High speed required. Why do we need high speed? Because we want to use it in more complicated blocks like A to D converters, for example. So high speed is an issue. In that case, we should be able to drive large capacitive loads. In that case, a typical architecture like this one, for example, so this is a basic comparator structure. This is an op-amp, right? You can use it like a comparator. That's okay. But the main problem is you have only this stage to drive the capacitive load. And using very large W over L ratios in M6 and M7 can be a problem, because then you are going to put extra loading on here. So to be able to solve this, you can use some sort of like cascaded inverters. So this stage in here, what it does is it first increases the gain, and while increasing the gain, you can increase the driving capability step by step. For example, if you are using some W over L ratio in here, then there will be some capacitive load in here. This M6 and M7 drive that capacitive load. For the next stage, you can use large W over L ratios so that you can drive a larger capacitive load. But while doing this, you don't want to change the output binary value. Because of that, you have to use even number of inverters. And while doing that, you can use a larger W over L ratio for this M10 and M11 to drive a larger load capacitance. So by this way, you both increase the gain and increase the driving capability step by step. So for example, you have some capacitance in here. M8 and M9 can drive that capacitance, which can be a large capacitor, but not as large as this CL capacitor, let's say. And this thing can drive some capacitance, but it's low capacitance. And in a stepwise way, you can increase the driving capability. If you find the overall gain of this structure as an exercise, let's find it as an exercise. There are 4 main stages. So A overall is A1, A2, A3, A4. A1 is obvious, minus GM, sorry, it's plus GM 1 or 2, arrow 4, arrow 2. A2 is minus GM6, arrow 6, arrow 7. A3 is a CMOS inverter, and we have solved this example before, I guess. But just to remember, it's going to be GM8 plus GM9, arrow 8, arrow 9. And A4 is minus GM10 plus GM11, arrow 10, arrow 11. So you have a huge gain, and you have a large drive capability. Most of the time, you use multi-stage structure for comparator approach. But one thing is, in fact, this is continuous time comparator. This is a continuous time comparator, but in some applications, in fact, in most of the applications, you may need discrete time version of that. Discrete time may be required, which means that you need to do some sampling and then keeping the comparator output stable for a while. This is especially useful in A to D converter design, because in that case, you are doing some sort of sampling So you can combine discrete design with this comparator design. And in that case, what you do is for this last stage, you use a latch instead of a simple inverter. So we will remember the latch structure later on. But if you replace this inverter architecture with a latch, with a clocked inverter version, then you do some sampling and discrete time converter comparator can be implemented. And we will see some examples of that.
Hocam,
Sure.
burada A1 eksi GM 1, 2 artı A2'ler olması gerekiyor gibi düşünüyorum ama şu V'nin
A1 should be negative, you say, right?
Evet.
Let's double check it.
Aşağıda pozitif.
Okay, let's check it. You're right. So this is, yeah, you're right. Thank you for the correction. So it should be negative because the input polarity is given in the reverse direction. I didn't notice that minus sign at M1 gate. Yeah, thank you for the correction. Okay. We have seen this architecture before. This was an hysteresis comparator, and I want to solve a numerical example on that to find the trip voltages. And I will show you that by using an inverter stage at the output or another gain stage at the output, you can achieve a better characteristic. So let's start with the structure. Kn, Kp values are given. So K and Kp are given, Vt and Vtp given. They ask us the positive and negative threshold points if the device lengths are 1 micron and W values are given like this one. And the current I5, the bias current is given as 20 microamp. So the current passing through here is 20 microamp, and they want us to find the trip voltages. Okay, so in the previous lecture, we have analyzed this thing in detail. So we have find that I6 is equal to W over L6 divided by W over L3 I3. And it's given like 5 in this case, because WL is 10, W6 is 10, W3 is 2, so it's going to be 5 times I3. And when you want to find I3 from the previous lectures, we have find such an expression. You don't need to memorize it, but you can drive it again if you wish. You shouldn't memorize anything in this lecture. But if you drive it, you will find it like this thing, which is also equal to I1. And you will find it as 20 divided by 1 plus 5, which is 3.33 microamps. I2 is equal to I5 minus I1, which is 16.67 microamps. And from here, you can find VGS1 as 2I1 divided by Kn, I guess. Square root of 2 plus Vtn1. Let's check it whether it's correct or not. VGS1 minus VGS2 times Kn over 2. Yeah, that's okay. And if you solve it, you will find it like 0.81 volts. Similarly, you can find VGS2 as 2I2 divided by Kn square root plus Vtn2. And if you solve it, it's going to be 0.94 or 95 volts. So from here, VTRP plus is equal to VGS2 minus VGS1, which is 0.14 volts. So what I do in here, I first start with the positive trip voltage. For the positive trip voltage, it is the point at which M2 turns on. And in that case, by using the current ratios in here and with the given parameters, I can find the difference between these two voltages to find the trip voltage, positive trip voltage. Similarly, we can find the negative trip voltage. So when you calculate the negative trip voltage, for negative trip voltage, you're going to find now I4 as 3.33 microamp, I1 as 16.67 microamp. And if you continue on the calculation, you will find that like VTRP negative will be minus VTRP positive, which is minus 0.14 volts. So as you see, although the circuit is quite complicated, the solution is quite straightforward if you understand how it operates. And here is the computer simulation of the same circuit. And as you see, positive trip voltage is somewhere around 0.1, consistent with what we have found in here. I mean, it's in fact somewhere in here, as you see, the positive trip voltage. It's not exactly matching with this line, but it's okay. And for the other one, it starts somewhere in here. So it's consistent. But as you see, the graphic is not very nice. I mean, in ideal case, you want something like this, right? Sorry. In ideal case, you should see something like this. So there are some deviations on the edges, especially in here and here. So you can improve it by using a gain stage at the end. So after this stage, for example, if you can add one more gain stage, your output signal, your output versus input characteristic will be much better, and it's going to much more look like a real Schmitt trigger. So how you can do that? Here is a solution. So this is the main amplifier, or main comparator. So this is hysteresis comparator. And these two stages are this one and this one. Gain stage, extra gain stage. And this part is for biasing. This is for biasing. In this particular example, we got single-ended output, but this is not a must. You can use a double-ended output as well. The only difference in here, we use a current mirror structure in here to copy the gain received from this part to here. So the extra gain stage gain, so a gain can be written as minus GM 8 or 9 arrow 8 in parallel with arrow 11. And this is defined as, of course, V out divided by VI1. Then we should put a positive sign in here, VI1 minus VI2. Okay. So depending on this gain stage, the output can be either inverting or non-inverting. So you have to be careful about the definition of the input. And I don't think that the input definition is clear in here. You have to clarify which part is positive, which part is negative. Depending on that, the output curve can be either like this or like this. You can make it both inverting or non-inverting. And the critical thing in here is your trip voltages are not going to change because trip voltage is related with this part and this part. And you are not playing with it. So trip voltage is not going to change. As you see in this new graphic, we still have the same trip voltages almost, except small variations. So keep in mind that the hand calculation is a first order one. And with a computer simulation, you can get a more accurate one. But when you do the hand calculation, you will find the same result. It's not going to change. But the good news is with this increased gain, you eliminate these regions. They look much more like real Schmidt trigger characteristic. Okay. So the moral of the story, if you are doing a comparator, you need a high gain. And for achieving the high gain, you are using an extra gain stage. This gain stage can be a typical one, like this one, M8 and M11, or it can be an inverter, a CMOS inverter to achieve a better gain, or it can be a switched CMOS inverter, like a latch, to have discrete time operation. So when you see a comparator architecture like that, please don't get confused. It can have different versions because you want to maximize the gain as much as you can. And there are different ways to implement regenerative comparators like Schmidt triggers in CMOS. So here's another example. It looks like a much simpler device design. So let's take a look at the structure and try to understand it. So we have two series NMOS transistors in here and two series PMOS transistors. They are sharing the same input at the gate, like this one. And we have some extra transistors. One of them is this NMOS M3 connected in this way. And symmetrically, we have another one, which is made of PMOS, but connected in here and in here. And this works like a Schmidt trigger. So let's try to understand how it works. So when V in is low, and you can always treat it like that because comparators are eventually behave like digital components. They provide binary outputs, so their inputs will be binary. The only thing that you care is their tripping voltage because you care about your sensitivity. So when the input is low, when you apply low signal in here, what happens is this M2 and M1 will be off. They are not conducting, okay? And M5 and M4 PMOS transistors behave like a switch, so they provide short circuit. But keep in mind that for a PMOS like this, when this node is floating, and this node is VDD, if you apply, ground at the gate, for example, what happens is this thing will work at VSD versus, sorry, ID versus VSD. I'm trying to draw. So this thing is definitely on because VSG voltage is larger than VTN. So it should operate on one of these curves, whatever. But the problem is the current is equal to 0 because this node is floating. So the only option is it's going to work at linear region with VSD is equal to 0, ID is equal to 0, which means that this node potential will be then VDD, and which means that M3 will be on. M3 will be on, but again, this node is floating. Source of M3 is floating. So it's going to obey the same thing. It's going to be on with 0 current and 0 VSD voltage, which means that this potential is VDD. It is on, which means that this potential is VTN. So this node will be at VDD minus VTN. But 0 current is passing. It's on the edge of conduction, but not conducting any current. So discussion for this PMOS transistors and this NMOS transistor is a bit different. Why? Because for the PMOS transistors, gate to source voltage is fixed. So you are following this line. But for M3, source is floating, which means that source voltage is not fixed. But I know that gate voltage is at very large value. So it should be on. So you can assume it like you have some parasitic capacitance in here, and you try to find the final steady state capacitance, the steady state voltage of this capacitance. And if you find it, you are going to find it like VDD minus VTN at steady state. Anyway, these are like, some sort of details. We are trying to understand the operation. So we are trying to find the output. Output is connected in here, as you see. So this says that my output is high or VDD. When input is low, Vout is high or VDD, as expected. Let's take a look at the other case. By the way, if you have any questions, you can stop me anytime. When I'm checking the chat box as well, whether there are any questions or not. Okay, when Vin is high, so now the story is a bit different. So let's clear it up. But the same, of course. When Vin is high, these two transistors will be off. They are not conducting. M2 and M1 are conducting a linear region with 0 current and 0 VDS voltage. So this means that this node is at 0 volts, which means that M3 is off. M6 is on, and it's at the edge of conduction. So this node will be at VTN, VTP absolute value, sorry. So when Vin is high, then M1, M2 on, linear, IDS 0, VDS 0, M6 is edge of conduction, IDS is equal to 0, VGS is equal to VTP absolute value, sorry, VSG. Let's make it consistent, okay. And this means that Vout is low at 0 volts. So this works like an inverter. So what does this mean? This means that when input is low, you have high output. When input is high, you have low output. But what is important for us is in between. We want to make hysteresis comparator. There should be some trip voltage. And let's find it. VTRP plus is the input voltage when M2 turns on. So when input is high, sorry, when input is low, this was off, and no current was passing. But when you try to increase the input voltage slightly, at some point, M2 will turn on, and you start getting current in this direction or in this direction. So when M2 turns on, it's for sure that there is some current passing through here. So trip voltage occurs, so this occurs when input voltage makes I1 equal to I3. Therefore, ID1 is equal to Kn1 divided by 2 VGS1 minus VTN1 square, which is equal to ID3 Kn3 divided by 2 VGS3 minus VTN square. So, assuming that VTN1 is equal to let's write it like this. So this means that Kn1 divided by 2, VGS1 is equal to input voltage. So it's going to be VTRP plus minus VTN1 square. And this should be equal to Kn3 divided by 2. And VGS3 in here is, look at it, this voltage minus this one. This is initially at VDD, and this will be, and this voltage is at the turn on equal to VTN. Sorry, this voltage will be equal to VDD minus VS2. VDD minus VS2 minus VTN3 square. And when M2 turns on, it's for sure that Vin is equal to, or VTRP is equal to, VTRP plus is equal to VTN2 plus VS2, because M2 is just turned on. So if you put this thing in here, if you put this result in here, the final solution will be VTRP plus will be defined as VTN1 plus Kn3 divided by Kn1 and square root times VDD divided by 1 plus Kn3 divided by Kn1 in square root. So the calculation seems a bit complicated, but in fact it is not. What you need to do is you just need to find the input voltage when this potential is equal to VTN2, because we are looking at the point at which M2 turns on. And right at that point, we know that no current passing through M2. So this current should be continuous. M1 and M3 should have the same current passing through them. So by using the equations related with these two conditions, you solve the corresponding VTRP. And we can do the same thing for the negative trip voltage. So for VTRP negative, can be calculated or derived, let's say, derived similarly. And if you solve it, you'll find it as Kn Kp5 divided by Kp6 in square root times VDD minus VTP5 divided by, so there's a mistake in here. It should be like this, I guess. Anyway, 1 plus Kp5 divided by Kp6 in square root. So please check this as an exercise. And the characteristic will be like this. So this is VTRP negative. This is VTRP positive, and you have the inverter characteristic as expected. And as you see, by using only 6 transistors, you can implement a hysteresis comparator. Hysteresis is critical for us. We want to have hysteresis comparators. Why? Because we want to implement noise immune circuits. We are using them for comparating purposes. So any noise at the input may result in undesired output characteristics. So by putting hysteresis, you eliminate the effects of that noise at the output. This is especially critical for A to D converters. You don't want your output to change all the time because of the noise. You want to eliminate the noise as much as you can. So that's why you need hysteresis. And keep in mind that for hysteresis, you don't necessarily have a very large change at the trip voltages. A small change is sufficient because you assume that you are implementing everything on IC. So you can eliminate the noise by using a small change at the trip voltages. Okay, so hysteresis is critical and we want to use hysteresis comparators. Okay, so let's continue. And as I said at the beginning, we have 2 types of comparators. One of them is continuous time. The other one is discrete time. And this is in fact desired in most of the applications because you don't want to do some sort of like real-time comparison. You just want to take the comparative output at some point and you want to store it for the next cycle. You are going to use it most probably in digital circuits like A to D converters. So sampling is critical. So in that case, you can just use latch structures. Do you remember the latches from 312? Something like this, as you may remember. So this is a sort of a latch, right? So when you write some high voltage in here, it's gonna stay there forever. It's not gonna degrade by the leakages on the capacitance or whatever. Why? Because if this thing tries to get slow, the inverter output will be very low, so it's going to push the voltage in here to high again. So it's going to store the data forever. And by using this thing in a switched version, like this, so this is enable signal. This is also enable signal. You can store the data and you can change the data. When you activate this enable line, you write the data to this point and you write the other data to this point by brute force. And when you disable this switches, the written data will stay there forever. We use this thing as a memory structure. So in fact, this is a comparator at the same time, some sort of a comparator. It can be used to have discrete time comparators. And this is the basic structure that you see in here. Instead of CMOS inverters, what they use is they use some current source and NMOS transistors, for example. What happens is when the enable signal is active, these two lines are disactive somehow, and you write the data here and here. When the enable signal is deactivated, output 1 and output 2 are not connected to the latch anymore. And by using this biasing, in fact, you have two inverters connected back to back. So this is one inverter like this one. This is the other inverter like this one. And they are connected back to back. So they store the data forever with this extra current signal. And you can show the same thing by using PMOS version, by using PMOS transistors. And it's, in fact, almost the same thing. So let's see how we can use it in comparator application. But in fact, before then, you can make a very complicated analysis on this, like, rise time and fall time, when you apply a step input, how the output will change, and so on and so forth. I'm just going to pass it. I'm just providing this thing for the sake of completeness, but you don't need to follow these derivatives line by line. But the idea is this. You have this less structure, one inverter in here, the other inverter in here. Outputs are connected to each other's input, exactly. So you can come up with a sort of a small signal model in here with some internal resistance and capacitance and the input signal. And you can relate these signals, input and output signals, to each other by using these dependent current sources. And if you solve it, as I said, you don't need to memorize or you don't need to follow this thing line by line. But the moral of the story is this: you can calculate the step response of this latch, which means that for this latch, let's say, when you apply an input like this, you expect an output like this, but it's not going to be exactly this way. This is in the non-ideal case, the output will change like this. And this region is critical because it's going to give the speed of your structure. And this is critical for speed. Let's say that you want to make an A to D converter with very high speed, then you need to go down and find this time duration, whether your comparator or the latch is compatible with that speed or not. And it is doable. I mean, I'm sure that you can follow these derivations, although you are not responsible from them. And eventually you can find the relation between output and input, and it's somehow related with the change in the input. And if you draw it, you see that depending on the delta of the input, the step response or the propagation delay changes. Smaller voltages, you have larger propagation delay. But if you apply high voltages, propagation delay is less. So you can imagine it like this. Again, the same latch. We have this, but while applying this input, this is delta V, let's say. We are playing with this delta V, increasing this thing or decreasing it. For small input changes, propagation delay is high. This means that decision takes more time. Your latch or comparator is not compatible with high speed for low input voltages. But when the input voltage is high, when you have large variation at the input, then the decision is very fast. And this is quite logical. Why? Because when the input is high, you can compare them very fast and you can say that whether the output is binary 1 or 0 right away. But when they are getting smaller and smaller, they are getting closer to the gray region. In that case, it takes a bit more time to make the final decision. Okay, and that's why we put the stage before the latch. So, moral of the story, the thing that you should keep in mind is this. For larger input signal, you get a faster response. And because of that, use a preamplifier before the latch. If you want to use a latch as a comparator, you should have a preamplifier before. It may sound a bit confusing at the moment. It may sound a bit complicated, but in a couple of slides, I'm going to show you some real examples, and you will see that this is just straightforward, not that much difficult. What I'm trying to show with these two slides is this. I mean, if you have the enough knowledge of mathematics and circuit theory to be able to find this propagation delay, and you are not responsible from it. I'm emphasizing it. In the scope of this course, you are not responsible from this derivation, but just know the result and just try to understand why do we need a preamplifier stage before the latch if we are using the latch as a comparator. Okay, so here is the implementation of a CMOS latch, a typical example. So this is a typical example. As you see, we have two inverters connected back to back. So this is inverter 1. This is inverter 2. What we do is, in fact, we connect inverter 1 and inverter 2 like this. And M7, M8, M5, M6 are, in fact, just switches. So this is, let's say, M7, and this is input. And this is M8. This is the reference voltage. Okay, you see. And M5, M6 are just for powering. So if you have a power, I'm not showing the ground and the whole structure, but M5, M6 provides that. Okay. M5, M6. So what happens is when the switch is active or phi latch is low, let's say, these are off. Sorry, maybe I should use this one. When phi latch is, let's say, low, these are not active, inputs are not connected. You power up the latch, they are shorted, and it stores the previous data. However, when phi latch is high, when you have high, this means that you deactivate the power lines. Powers are not provided in here. these are shorted. So now you are comparing input with the reference, and depending on that, we output plus and we output minus takes a value. When input is larger than the reference, for example, we output plus will be high, or vice versa. We have to double check it. The other one will be low. Depending on the difference between V in and V ref, you make a comparison, and the latch decides Q and Q bar depending on their difference. When you activate the power line in the next cycle, when you make file latch low, then it amplifies this difference and makes Q and Q bar to their desired binary value, either high or low. So this is some sort of a comparator structure, and this is a very simple one. You know, we have to discuss a bit more on this thing, I guess, and we will see a bit more complicated architectures on that with offset voltage distribution and so on and so forth. So we can stop here for today, and in the next lecture, we can continue with more discussion. So please go over this material, and if there's anything that you didn't understand, please warn me so that I can explain it on the next lecture.